we are looking forward to listening to you. Just one more remark that we have rescheduled Professor Sandeep's talk to two consecutive talks with a break in between. Okay? So, yeah, please. So maybe, sir, you can share your screen and
okay, thank you, Josna, for the invitation and the kind introduction. So let me just share the screen. Is it visible?
Yes, yes, it is.
So shall I begin?
Yes, please, yes.
Okay, so good morning. So I'm going to talk about some, it's basically going to be an introduction to some of the modern tools in the study of electric PDEs. Okay. So the material is not going to be your standard MSc PDE course material or BSc. Okay, so this is just to give you some glimpse of some of the maths which is used in the study of PDEs. Okay. Okay, so the problem that I'm going to consider, so this I have written something here, so elliptic PDEs, so write elliptic PDEs. I'm sure you must have already seen some of these things. And the prototypical example, or what we are going to consider, is the operator Laplacian, okay, which you know that it is going to be d square by dx1 square plus etc. plus d square by dxn square. Okay? So this is the operator that is in Rn. In Rn, I denote a point x by x1 etc. So we are going to consider the equations PDEs related to the Laplacian. Okay? So for example, we will be interested in problems like say Laplacian of u is equal to f in a domain omega, or let me call it as a ball, a B, where B is a ball. Okay? Ball in Rn. And you will have a boundary condition, for example, for simplicity, let me call it u equal to 0 on boundary of these kind of problems. Okay. So this is what I wanted to study. Okay. So here, as I wrote before, Laplacian is the d square by dx1 square plus d square by dx2 square plus d square by dxn square. So in these kind of problems, an f will be given. The task is to find a u such that u solves this equation, that is Laplacian of u is equal to f. Okay? So I am putting here a minus Laplacian, that is just to for some convenience. Okay? So we can do it. Okay? So when you are in R1, when n is equal to 1, okay? So this becomes Laplacian becomes the second derivative, right? Becomes the second derivative. Second derivative operator. Okay. So, or the corresponding problems become, I can state as something like minus u second derivative of is equal to some f. Maybe I will put u second derivative of x is equal to f of x. Maybe in this case, I will write, for example, x is in some interval ab. Okay, and I will have a boundary condition. I have written here that u is equal to 0 on the boundary. So the boundary of AB is going to be A and B. So I will assume that u at A is equal to 0. That's also equal to u at B. So what I am going to do is that a simple version of this equation which I wanted to study is this. Okay? And that is an ODE actually, as a boundary value problem. I'm sure you would have studied about this problem in your ODE course. And you have seen how to write you can integrate this and you can get the solutions and so on. So just now, you call it by name. Yeah. So this is the equation that we wanted to study. So yeah. So this ODE problem, you have seen many ways of solving it. In fact, you can just integrate it. U second derivative is equal to fx. You can integrate and then you will get u prime, and then integrate once again you will get u. Okay. Then you can actually write a solution of this. Okay? But I'm going to look at this problem in a more theoretical way so that I can adapt those things to study the case of general problem, which is the Laplacian, which I have mentioned here. Okay, so that is what I am going to do. Okay? So first, let's assume u is a solution of this ODE minus u second derivative of x is equal to f of x. Okay. This is in the interval x is in AB, and u at A is equal to 0, that is equal to u at B. So what do I mean by u is a solution? That means u is twice differentiable and the second derivative is equal to f. Okay. So given f is given, so u is going to be the solution of this equation. Okay. Now what I wanted to see is, so u is a solution, I want to see some consequences. Okay. So let me just take a function, let phi is a C1 function with compact support in the open interval AB. Okay. So by this what I mean is that phi is going to be, phi is say continuously differentiable, that is phi is differentiable, okay, and phi prime is continuous, and I have this interval AB here, and phi vanishes outside some interval here. So in particular near A and near B is going to be okay, so that's what I mean by C1 function with compact support. Okay. So assume that u is a solution of this equation. Now I start with an arbitrary phi. Okay. Then I can multiply this equation by phi. So then you will have minus u second derivative of x into phi of x. Okay. That is equal to f of x into phi of x. Okay. Now what I do is that I am going to integrate this relation from integral from A to B. I am going to integrate this from A to B. Okay. Now I can use the integration by parts on the left hand side. Okay. So then the left hand side becomes integral of from A to B. Okay. One derivative I can push to phi, so it is going to be u prime of x into phi prime of x. Then there are terms like u prime into phi at B minus u prime into phi at A. But phi is 0 at both A and B, so there won't be any boundary terms. So this is going to be equal to finally this. This is going to be integral A to B f of x into phi of x dx. This is what you are going to get at. Okay. So that is what we have seen is, so that the solution is that if u solves this equation, minus u second derivative is equal to f in AB. Anything? Can I continue?
No, I think somebody unmuted it. It's fine, please continue. Yeah.
So if u solves this equation, u in B with the u at A is
Please, participants, please mute yourself. Yeah, please continue. I think Sandeep has also been muted. Please unmute him.
Yeah.
Yeah, okay. It's fine.
Yeah.
Sorry.
If U solves U second derivative is equal to F in AB and if U is a solution of this equation, then for all P in C1 function with compact support in the interval AB, I have this relation that what I have seen here. Okay? That means integral from A to B, U prime of x into P prime of x dx. That's going to be equal to integral from A to B f of x into phi of x dx. Okay? So this is a consequence that if U solves this equation, then you will have another consequence like this. This is true for all phi. Okay? Now let me try in the other way. So suppose U is it's a C2 function, U is C2 and satisfies this identity. That means integral A to B U prime of x into P prime of x dx. That's going to be equal to integral from A to B f of x into P of x dx. Okay. So suppose U is a C2 function and satisfies this, then you can, again this relation you can integrate by parts again, and this will lead to and satisfies this for all phi element of CC1 of AB. Okay. Then this will imply that you will have integral from A to B minus U second derivative of x into phi of x dx is equal to, on the right hand side is the same, integral A to B f of x into phi of x dx. Okay? And combining these two integrals, this will imply that integral from A to B, and I can put it in bracket, U second derivative plus f, this into phi. This integral is equal to 0 for all phi element of CC1 of AB. Now you have so now it's a result in integration that suppose you have from integral A to B some g into phi. So I will put it in integral of g into phi is equal to 0 for all phi. For example, it can be even in CC infinity of AB. Okay? CC infinity of AB. Then this implies that g has to be equal to 0. Okay? So for example, it is very easy to see, for example, when g is going to be continuous. Okay? So this is the in interval AB. Suppose g is not equal to 0 and suppose g is continuous, then g has to be either positive or negative. At some point it is positive, suppose. Okay? Then by continuity in a small neighborhood it is going to be positive. Okay? So and now you can get a phi which is supported somewhere here like this. Okay? You can explicitly write down those functions. And then you can integrate from integral A to B g into phi. And then you see, you can see that g into phi it is supported in this region where both g and phi are strictly positive. So this cannot be 0. Therefore, it will give a contradiction. Okay. So what I am saying that if you have function g and its integral against any c infinity function with compact support is 0, then that function has to be identically 0. So this is a result. This is what we are going to use. Okay. So let me recall and see. I assume that U is a C2 and satisfies this kind of condition for all phi. Then I can integrate by parts and I am reaching this kind of a condition. Okay, and that will imply you treat this as my G.
अभी 2-3 सुनाकर आया हूँ.
Hello. I think yeah. Please don't disturb.
Yeah.
Please continue. Sorry for
Yeah.
that.
Yeah. Yeah. So then I will have this relation. This will imply, so using this result, you will get that. So here this quantity u second derivative plus f, that is going to be equal to 0. U second derivative plus f is equal to 0. Or this implies that minus u second derivative is equal to f. Okay. So the conclusion is that u is a, I am taking a u is a C2 function. Okay, u is C2. Then then the following are equivalent. The following are equivalent. So the first one is u solves the differential equation minus u second derivative is equal to f in the interval AB. Okay? And the second one is u satisfies integral from a to b, u prime into phi prime is equal to integral from a to b, f into phi. This is for all phi element of CC1 of AB. So these two things are equivalent, provided u is C2. But note that you have to remark, the advantage is that the second two involves only the first derivative of u. First derivative of u. That is, okay. We can talk about 2. We can talk about the condition 2 when u is in, say for example, a C1 function, C1 in AP, when u is in Somaiya, but need not be C2. Need not be C2. Okay. So, but if you want u to be a solution of the equation, it has to be twice differentiable, and a C2 function, and if u is C2, this and these are equivalent. So, but this involves only the first derivative. Okay. And we know that, yeah, so now the question is that to define this, it involves only the first derivative of u. Okay, so what I'm trying to say is that, so if what I wanted to do is that I wanted to call a function u is once differentiable, or if it is C1, and if it satisfies this kind of an identity, then I wanted to call it as kind of a weak solution. Okay, because when u is C2, and that identity will tell you that it is indeed a solution. Okay, so but just when that identity is satisfied, so I would like to call it as a solution in some form. I will call it as a weak solution. So our aim or we will define u element of C1, maybe AB, is a weak solution. Weak solution of the equation minus u second derivative is equal to f in AB if it satisfies integral from a to b, u prime into phi prime is equal to integral from a to b, f into phi for all phi element of CC1 of. So earlier, if you want to be a solution, it has to, so from the previous discussion, we know that I'm just trying to call the U element of C1. That means it's only once differentiable. It's a weak solution of the second order equation, if it satisfies this. Okay? This is my aim. Okay, so let's see that. So then note that from our discussion, if we can find a weak solution, and if it happens to be C2, then you will indeed be a solution. Indeed solve minus u second derivative is equal to yeah. Okay. So now, so that means I have defined what is known as a weak solution, weak because it's satisfied in a weaker sense, and what I am trying to call, it involves only the first derivative, or a once differentiable function. I am trying to call it a solution of this. Of course, if you want u to be a solution in the classical sense, it has to be twice differentiable, and my weak solution is only need to be only once differentiable. Okay? So the strategy is that, can you find weak solutions? Okay? So when you are trying to study these kind of problems, the modern strategy is you somehow try to find a weak solution. Okay? And the advantage is that when you are trying to do a weak solution, you will be able to use a lot of your modern mathematics. And then after finding a weak solution, then try to see whether it is indeed twice differentiable. The second part is called the regularity theory. Okay? And that's a separate story. What I am going to see is that whether you can indeed find a weak solution. Here I have told that U is I defined U element of C1 is a weak solution if it satisfies this kind of characteristic. So the question is, does weak solution exist? Solution exists for a given f. That is, what we are asking is, does there exist a U element of C1 satisfying integral from A to B U prime into phi prime, that's equal to integral from A to B f into phi for all phi element of CC1 of A. Given an f, can you find a U which is in C1 which satisfies this, or can you somehow assure that such a thing exists? This is the question. Okay? So this question, I just wanted to make some remark here. Look at in this requirement, there is a left hand side and a right hand side. Okay? So look at the right hand side, RHS. Okay? RHS, this has to be true for every map. So what I wanted to observe is, the right hand side, the map is phi going to integral from A to B, f into phi. Okay? For any phi, this is the map. Okay? And this map is linear. That means if phi1 plus phi2, suppose I call that is, suppose I defined L of phi is equal to integral of A B into f into phi, then L of say some A times phi1 plus phi2 is equal to A into L of phi1 plus L of phi2. And in appropriate spaces wherever we wanted to define. That means it's a linear map. Okay? So, and now look at the left hand side. You can look at the left hand side. That is the map, basically something like integral from A to B, okay, U prime into V prime, okay. This looks like this is bilinear in U and V. So we may suspect whether it can be an inner product. Question is, there can be an inner product, maybe inner. That is the question. So more abstractly, this requirement, it turns out to be, what I am asking is, so there is a right hand side is RHS is some linear functional, right? And the left hand side LHS is an inner product. So if you have learned some functional analysis, then you will immediately understand that there is a theorem in functional analysis which connects linear functionals with inner products. Okay. So do you know what that theorem is? Representation theorem. Okay, good. Okay. So what does it say? So the representation theorem tells you that, okay, representation theorem, which tells you that, let H be a Hilbert space, Okay. So with inner product, say like this. Let me consider for simplicity it's a real inner product space. Okay, let's be a Hilbert space with inner product. Then for any a linear functional L, that means L is in the H star. That is a linear functional and it is continuous linear functional. L is in H star. There exists a unique, say, X element of H. Okay? It's in H such that L of y is going to be equal to inner product of y with X for all y. That means the linear function L is given by an inner product. Okay. So now what we see is that it is our requirement. This is what I wanted. Okay. So this is what. So that means f is given. So integral a to b f into phi. So phi goes to this. That's a linear function. And the left hand side, it looks like it's a bilinear form. So it looks like an inner product. Okay. So the question is exactly the same. Or right hand side is a linear function. Can it be given by an inner product? That's precisely the question. Okay. So the only thing what is missing here is we need an Hilbert space to apply this. Okay, this theorem. Okay. So right now I am dealing with all functions phi, which is in C1 function with the compact support and so on. Okay. So how do I make it? A linear function? Okay. So that is what I wanted to see. Okay. So the question is now, can we apply this theorem to get our result? So now first note that our inner product is like, so we need our inner product product looks like say integral from a to b, say u prime into p prime. So this should be ideally the inner product of u and v. Okay? So can you have something? So what we are going to do is that first consider the space, say C1 function with the compact support in the interval. Okay, and I'm going to define.
No.
Yeah. Hello.
Sorry, sir.
Okay, not to me, right?
Not to you, sir. Sorry.
Right. So define for u comma phi element of C1 function with compact support in the interval AB. Okay, I'm going to define something like an inner product of. This is what I wanted to get. Inner product of this is like integral from a to b u prime into phi prime. This is what I want. But C1 function with compact support, and it may not be that. So what I am going to do here is I am going to define for u element of CC1 of AB. Okay? I am going to define norm of u is equal to integral from a to b modulus of u prime square all to the power 1 by 2. Okay? Then this norm is not so CC. This is a norm. This is a norm in the space CC1 of AB. Okay? But it is not complete. It is not complete. It is not complete. Okay? So what I am going to define is, so you know that any non-linear space can be completed. Okay? So what I am going to do is that I am going to define a space H10 of AB. Okay? AB. This I am going to define as H10 of AB is the completion of CC1 of the AB with respect to the norm. Norm of u is equal to integral from a to b modulus of u prime square all to the power 1. Okay. So then this is going to be, then you can see that then H10, this completion, this AB is a Banach space. And indeed it is an Hilbert space. Okay? Hilbert space. Okay? So that means there is an inner product which induces the norm, and that inner product will be given by the inner product of u into some phi that is indeed going to be integral from a to b u prime into phi prime. So this completion is going to be an abstract object, but you can write it concretely what it is. In fact, if you know what is known as an absolutely continuous function, then actually you can show that you can define it using absolutely continuous function. Maybe I will just make it as a remark. In fact, one can characterize characterize this H10 of AB as the set of all U from AB to R such that first one is U is absolutely continuous, okay. So I hope you people know what is absolutely continuous. So I just want to remark that it is not that modulus of U is continuous, no, sorry, and it's a better property. I'll make some remark. And second property is that U at A and that's equal to 0, that is going to be U at B, okay. And the third one is, so absolutely, it's known that absolutely continuous functions are going to be differentiable almost everywhere. Not at every point, but it will be differentiable almost everywhere. And you also need that integral A to B modulus of U prime square is fine. Okay. So this space H10 of AB is the collection of all absolutely continuous functions in the interval, which vanishes at both endpoints, and its derivative is square integral. So you can precisely characterize that completion. Okay. So let's not bother too much about this. So essentially so this space is actually going to be the completion of CC1 of AB, or in other words, the CC1 of AB is dense in this space. Okay. So there's no issue. Whatever I wanted to prove, I can prove it with the CC1 of AB, and then hopefully I can take a limiting argument and get the conclusion for everything. Okay. So this is the idea. Okay. So now, yeah. So another remark is absolutely continuous. U is absolutely continuous. Continuous. If and only if it satisfies the fundamental theorem of calculus. Fundamental theorem of calculus. Okay, perfect. What does it mean? What is fundamental theorem of calculus? Basically, you will get the function u of x is going to be equal to integral u of a plus integral from a to x u prime dt. This is the fundamental. That means basically you can get by integrating u prime. Okay. So absolutely continuous functions have this nice property that the fundamental theorem of calculus holds. In fact, they are equivalent. You can show that. Okay. Yeah. So you have this kind of a property. So what I wanted to tell you is that this H10 AB consists of absolutely continuous functions, and you know that absolutely continuous functions are differentiable almost everywhere. So indeed, this kind of a formula that this holds for all functions in H10 because they are all differentiable, not at every point, almost everywhere. So everything can be made up. Okay. So now what I can do is that once I have this definition, I can try to apply the representation here, okay, in this space to get that. Okay. So our aim is, as usual, as before. So the Hilbert space is this. So now I will modify my definition of weak solution. Weak solution. Earlier I have defined in the beginning somewhere, I have written aim. Yeah. We define U element of C1AB is a weak solution of this. That means U was a C1 function. Okay. And that was only needed because the definition requires only the first element. Now, even if the functions are absolutely continuous, they are differentiable. Okay. So I can relax the definition further, and I am modifying the weak solution as, so a U element of H10 of AB, which I have defined just now, is a weak solution of minus u second derivative is equal to f in AB with u at A is equal to u at B equal to 0 if it satisfies integral from A to B u prime into phi prime is equal to integral from A to B f into phi. This is true for all phi in H10 of A. Now the advantage is that this H10 of AB, that is a Hilbert space. Okay. So now, this is like, so the left hand side, this is the inner product, and the right hand side is linear. Okay. So let me see the right hand side. Let L from H10 of AB to R. Okay. They be given by so look, that f is given here. Okay, so integral from A to B f into P. Okay. So then we know that L is linear. Okay. Now the question is, if I want to apply the reciprocation theorem, it cannot be applied for any linear functional. They have to be continuous linear. Okay, is L continuous? That means what we want to check. We want to check whether so L of some phi. I want to see modulus of that is less than or equal to some constant into. Does there exist a constant such that this is going to be this into normal? If I have something like this, that will tell you that L is continuous, and hence L will be a candidate to apply the representation. Now, what do I mean by this? Okay. So this implies that whether I can have integral from A to B f into phi. Can I less than or equal constant into norm of phi? I have already defined. That is going to be, I note down here. Yeah, this was the norm. Okay. So the question is, when I replace this, then this is going to be integral A to B phi prime square to the power 1 by 2. Can you have that kind of an inequality for all phi? Now first note that on the left hand side, first of all, I am just trying to see whether I can prove such a thing. Modulus of integral from A to B f into phi. This I can write it less than or equal to, okay, I can integral from A to B modulus of f into modulus of phi I can put. This I can apply the Cauchy-Schwarz and I can get it as integral from A to B mod f square to the power 1 by 2, this into integral from A to B modulus of phi square to the power 1 by 2. Okay. Now f is the given function in the inequality, in the problem. So this I can treat it as a constant into integral from A to B modulus of phi square or to the power 1 by 2. So my question was this. So that means integral A to B f into phi, can I estimate it with a constant times integral A to B phi prime square? But a simple calculation, what it has given is, I can estimate on the right hand side something which looks very similar, but it is phi square, not phi prime square. Okay? So that raises the further question. Okay? Can we have an inequality like this, integral A to B modulus of phi prime square? Can you get it less than or equal to integral A to B phi square you have, I want to get phi dash square. Okay? So the question is whether you can have integral A to B modulus of phi square. Can you get it this a constant times integral from A to B modulus of P prime square. So if I can have such an inequality, then it will tell you that the left hand side, right hand side is going to be indeed a linear function. Okay, so I am going to show that this is possible. Okay, so that's the theorem. There exists a constant c greater than 0 depending only on a comma b. AB is the interval. AB such that integral from a to b modulus of phi square is less than or equal to constant times integral a to b phi prime square. Phi prime square for all phi element of say h1 0 of AB. Now recall that this h1 0 of AB is the completion of C infinity function or C1 function with compact support. So if I can prove such an inequality for C1 function with compact support by a density argument, you will get this kind of a result. Okay? So I am just going to prove this. It is going to be quite simple. Okay? So let phi element of h1 0 of A. And I have already, or let's put it as phi is a C1 function with compact supporting A. And it is enough to prove for that. Then we have by fundamental theorem of calculus, you see phi at x minus phi at A. Phi at A is 0. So you will get phi of x is going to be equal to integral from A to x phi prime t dt. Okay? So therefore, what I will get, this implies that modulus of phi of x, that is going to be less than or equal to integral from a to x modulus of phi prime t dt. So this is less than or equal to, I can write integral from a to b modulus of phi prime t, this into 1 into dt. Now I can apply the Cauchy-Schwarz. This will imply that integral from a to b phi prime t, okay, is modulus square all to the power 1 by 2. This into integral of 1, square is 1, so it's integral of b minus a, and you will b minus a to the power 1 by 2. You just integrate the function 1. This is true for every x. So I have for every x, this is the case. So now I can integrate this relation over AB. Okay? So this will imply that integral from A to B modulus of phi x square dx. Okay? So phi x is this. So phi x square is, you have to square here. So you will get, this is going to be less than or equal to b minus a into, and you have this integral square. And when you are, this is a constant, right hand side is a constant. So if you integrate it, you will get just a b minus 1. If you put both these things, you will get b minus a square into integral a to b modulus of p prime square. Okay? And that's exactly, this is a constant c, which depends only on a and b. That's exactly what we wanted. Okay? So it's actually true. So that shows that, so this implies that the map phi going to integral from a to b f into phi is a linear function, functional on h1 0 of AB if. So what is f is involved here? So I have shown here somewhere before. There is only that f, the only requirement that if f has to be in L2. Okay? So for example, if you can use, for example, if f is in say continuous function on AB or something, or if it is in L2, then it is trivially true. Okay? So the map, this map is going to be a linear function. It's going to be it's a linear function on AB and is continuous. Okay, so therefore, by Rees representation theorem, there exists a unique U element of H10 of AB such that this linear function such that L of phi is going to be equal to inner product of phi with E. Okay, for all phi. So this implies what? L of phi is integral from A to B f into P. That is going to be on the right hand side, the inner product is integral A to B U prime into P. Okay, and this implies that U is a weak solution. U is a weak solution. Okay? That means there is a weak solution exists actually for this problem. That is what we have. That is U is a weak solution. Weak solution exists for this problem. Problem for any f which is in say continuous in AB, or more generally for f is in what is known as the L2 of AB. Okay. So this is what we have seen. So right now what I have done here is that I wanted to study a problem like this, minus U second derivative is equal to f in AB, okay, with U at A is equal to U at B equal to G. Okay. So this is the classical boundary value problem. You know how to solve it. So what I wanted to do is that I want to use some maths and try to study this. Okay. The idea is that those techniques can be used to study the PDEs. Okay. So the first thing what I did was I defined what is a weak solution. What is a weak solution? Weak solution, and that was basically involving a function which satisfies this U prime into P prime is equal to f into phi for all phi in CC1 of AB. Okay. So that the advantage is that when you talk about a weak solution, it involves only this first derivatives. Okay. So then the question was, does there exist a weak solution? So the next what I addressed was the weak solution exists. Okay. Weak solution exists. So if I have defined something and if there is no way of finding it, so it's not of much use. Okay. So I have defined a weak solution. Okay. And that weak solution, what I have shown is next thing that would be indeed that weak solution exists. So what did I use to prove that weak solution exists? I used some functional analysis, right? And more importantly, representation theorem I used to show that there is a weak solution. And in the process, I had to introduce a space, which is the completion of the space CC1. I introduced something like CC1 of AB. Okay. I introduced a space. And another thing which I wanted to do was, I wanted to introduce, prove an inequality. Okay. I proved an inequality something like this. Okay. So I will just write it here. And we proved an inequality which says that integral phi square is less than or equal to constant times integral from A to B, phi prime square. Okay. So these are the main steps we proved, introducing this function space and proving an inequality. Okay. And once we did that, you can straight away apply your functional analysis. So we sort of left the theorem to get the existence of a weak solution. Okay. Now we found a weak solution, And then there are ways to prove that that weak solution is indeed twice differentiable and it satisfies the equation if f is continuous. Okay. So I am not giving that details right now. The focus is just to prove that there is a weak solution exists. Now, whatever I have done is a very baby version of a more general thing. So in the next lecture, I am going to introduce a more general form of these spaces, what are known as Sokolov spaces. Sokolov space. Okay. I will do it in a systematic way in the next class. Okay. So here I was giving a one variable motivation. And once you define Sokolov spaces, it's a very important thing that to prove these kind of inequalities. There is a generalization of this in the PDE context, what is known as the Poincare inequality. Poincare inequality. And there are more general inequalities in these kind of settings, what is known as the Sokolov inequalities. So the purpose of working with this kind of simple ODE was just to show that there is a notion of weak solution, and finding that weak solution, what is there involved? What involved is you want to find the right function space, and then you may need some inequalities and so on. Okay. So this is what I will be doing it in the next class after the break. Okay. So I will introduce what is known as a weak derivative. And using that weak derivative, I will define what is known as the Sokolov space, and I will indicate these inequalities in that context. Okay, and then I will show that even in that context, we can define a weak solution, and we can prove the existence of a weak solution. Okay, so I think I will stop here now, and we will continue after 10 minutes. If you have any questions, so from whatever I did so far, so please feel free to ask.
Sir?
Yeah.
Sir, can we find the weak solution using the fact that norm of the linear function will be the norm of u?
Norm of the
Linear
not the linear functional. You see, norm in the space, right?
No, sir. That regionally dependent theorem also says that norm of the linear functional must be equal to.
Yeah. That is true. That is true. Yeah.
So
that
norm
will
of
go here also.
yes, norm of u is equal to norm of L.
Yeah. So in this context, when you use that, you see, I'll tell you. Okay. So what does the representation theorem says? So you will have L is there, right? L is given by inner product, right? With some x. L of y is equal to inner product of y with the x. And what do you have? Norm of L, right? That's equal to, that's what you are telling?
The norm of u will be norm of that linear function.
Yeah.
So it gives us that any weak solution which satisfies that necessarily norm will be that vector.
Yeah, exactly.
So the converse, when we can say about the converse statement?
No, converse is what?
That if norm will this norm of u is equal to norm of L, then u is a weak solution.
No, that you cannot say.
So see, any other extra condition
norm of u is equal to norm of something, that is a very simple thing. Okay.
Yes.
Yeah, but being a solution, that involves more.
Yes, sir. Can we impose any extra conditions? Was there any result like that, sir?
No, not really. Yeah. You see, look at even in R2, you say that some norm is the same. That involves, norm means one entire circle is there, right? Norm is equal to norm. So there are plenty of choices.
Yes, sir. Yes.
Right?
Yes.
So you cannot expect. So you are in fact working in an infinite dimensional space. So just saying that norm is something, that only means that your solution is on some circle. That's all you will get. Okay? But then you have to search on that circle who is the solution.
Okay, sir, fine. Another question is, sir, so we are getting weak solution in C1 space, not in C2 space. So what kind of, why it is not differentiable, that what certain kind of problem were there with U-dex?
No, you see, I introduced the weak solution, okay. So finally, I did not get the solution in, you see, it is not even use a weak solution, okay, weak solution, and which is, I did not even find in C1C, okay, so C1C of AP, in fact, it is in the completion of that, okay, fine. So U is actually, this is actually going to what I saw is a U is absolutely continuous. Absolutely continuous. Okay. Right now what you can prove here is that U is absolutely continuous. That's all you can prove, what you found. Now, you can, so now later on, there are other tools. For example, suppose you can prove that F is going to be, say, continuous. F is continuous on AB. Okay. Then you can show that there are some other ways of doing it, but it requires some work. You can show that, in fact, U is actually U is C2. Okay? U is C2, you can prove. Okay? You can prove that, but it requires an argument. Okay?
Okay,
So
sir.
this part, even when you do PDE, it's a very serious problem, and it's what is known as the regularity problem. Okay, so it requires more argument to prove that. So that's a separate story. So what you do is that you make sure to find a weak solution. That means a solution in a more weaker sense. After that, you actually try to show that they are indeed differentiable. Then you will be able to do the integration by parts in the reverse order, and then you will be able to show that they are indeed the solution. That is the strategy. Okay?
Fine.
Any other question?
So, I think if there are no questions, then we can take the break and resume at 10:40.
Yeah, 10:40. Another 6 minutes.
Yeah, yeah. Thank you for a very nice introduction. Please, yeah.
Yeah, so I will just start. So I'm going to start what is known as weak derivatives. So browse please. So again, first I'm going to define what is a weak derivative. Again, I'm going to start with let U is a, say, continuously differentiable function on an interval. Okay. Then that means that we know that U prime exists, and U prime is continuous. This implies that for all phi which is in CC1 of AB, okay, so I can have integral from A to B U prime into phi. That is going to be equal to, I can do integration by parts, and I will get, this is going to be integral A to B. This derivative I can push into phi. That is going to be U into phi. Okay. So what it says that if U is a C1 function, the derivative will satisfy this U into phi, this relation. U prime, integral of U prime into phi is going to be minus of integral of U into phi. Now, suppose there exists a function, say function V, say let me assume that's a continuous function, V in a continuous AB, such that, okay, so integral from A to B, V into phi is equal to minus integral from A to B, U into phi prime. for all phi. All phi like a CC1, C1 function with compact support. Suppose you know that U prime satisfies this, V is equal to U prime satisfies this. Okay. Now suppose there exists a V which satisfies this. Then this and this, say I can put it as 1 and I can put it as 2. Okay. Then from 1 and 2, from 1 and 2, from 1 and 2, we know that the right hand sides are the same, so therefore you will get integral from A to B, okay, U prime minus V into phi equal to 0 for all phi in CC1, okay, of AB. So this implies that this is true for all phi. So using the argument which I mentioned in the previous class, this implies that U prime minus V equal to 0, or equivalently U prime is equal to. So what does it mean? What that means that U prime is the that is U prime is the only function, which satisfies 2 if U is differential. U is differential. So therefore, instead of a U derivative, I can classify with this relation, right? This kind U prime satisfies this. So that means U prime will satisfy this relation. Okay. So my aim is to call. So if such a V exists, then we will say that it's a weak derivative. Okay. So our aim is, but maybe it is possible that U may not be C1, or may not be differentiable, but there exists a V satisfying the relation integral from A to B U into phi prime is equal to minus integral from A to B into P for all phi. So it is possible that such a thing exists. Okay. So that is, so if such a V exists, we would like to call such a V as the weak derivative. It is possible if U is differentiable, continuously differentiable, then this identity will be satisfied with the V is equal to U prime. But even if U is not differentiable, it's possible that there may be some V which satisfies this. In fact, later on we will see that if such a V exists, it has to be unique. Okay? And if then such a thing we are going to call as a weak derivative. That's what we wanted to do. Okay? So now this is not only in one variable, I can define it in any dimension, especially because we are going to do PDE. Okay? So I am going to define, I can give this definition in any general space. Okay? So for that, I am going to give some notations. Okay? So omega is going to define, for me omega is going to be a bounded open set, or just an open set, in Rn. Okay. A point x is in omega, I will denote by, say, x is equal to x1, etc., xn, there are in coordinates. Okay. Then, are you familiar with what is this L1 of omega or Lp of omega? L1 of omega is 1 by 2 pi r square. L2 of omega is 1 by 2 pi r square. L3 of omega is 1 by 2 pi r square. L4 of omega is 1 by 2 pi r square. L5 of omega is 1 by 2 pi r square. L6 of omega is 1 by 2 pi r square. L7 of omega is 1 by 2 pi r square. L8 of omega is 1 by 2 pi r square. L9 of omega is 1 by 2 pi r square. L10 of omega is 1 by 2 pi r square. L11 of omega is 1 by 2 pi r square. L12 of omega is 1 by 2 pi r square. L13 of omega is 1 by 2 pi r square. L14 of omega is 1 by 2 pi r square. L15 of omega is 1 by 2 pi r square. L16 of omega is 1 by 2 pi r square. L17 of omega is 1 by 2 pi r square. L18 So LP of omega is, strictly speaking, all functions whose mod f to the power p. This is finite. Okay, and it's a very loose definition. More precise definition, you have to go to the equivalence class and so on. So just for the working convenience, you take it as LP is nothing but all functions whose pth powers are integrable. Okay, and this is going to be a non-linear space with the norm is going to be this to the power 1 by p and so on. When p is equal to 2, for example, L2 spaces, these are Hilbert spaces. Okay? Hilbert spaces. Hilbert space. And you must have learned in your measure theory course many of these details about these LP spaces and so on. Okay? And so now I wanted to define what is a weak derivative. Okay? So let me just define what a weak derivative is. So we can define weak derivatives. So look at this relation. I want this kind of a quantity. Okay? So I need integrability because you see phi is a function with compact support. Okay, so I need only integrable. V has to be integrable on that compact. Okay, so I just need something like a L1 log of omega. So this is going to be set of all u. Okay, from omega to r. Okay, such that. So for any compact set, set, K subset of omega, okay, U is in L1 of T. That implies what? So you have a domain here. If you take any compact set and this function modulus of U is going to be integrable, or it is integral is fine. So locally to L1 log just integrate. So it may not be in L1 of omega. That means if you integrate modulus of function over the entire omega, it may be infinity. But when you integrate on any compact set, it is. Okay. So one can easily see that, for example, continuous functions on omega. This is a subset of L1 log omega. Okay. What is the reason? Because if u is in a continuous function on omega and k subset of omega is compact, okay, then we know that modulus of u of x is less than or equal to some c for all x in k, because continuous functions on compact sets are bounded. Okay, so this implies that integral over k modulus of ux is going to be less than or equal to integral over k, the constant function c, and which is finite. Okay, so continuous functions are all there, and it is going to be a large class. The only demand we make is that when you integrate on any compact set, and it should make sense. That is, they are the class of functions what are known as the L1 log. Okay. Now with this definition, I can define what a weak derivative is. Formally, definition. Okay. We are doing PDE, so that is why we need partial derivatives. That is why I am doing now in Rn. Okay. So let omega be an open set in Rn, and U is an element of L1 log omega. Okay. That means a function where modulus of U is integrable on any compact subset of omega. Okay. Then we say that a function V element of L1 log omega is the weak say ith partial derivative, right? Partial derivative of U if integral over omega u into d phi by dxi. Okay? That is going to be equal to minus integral over omega v into phi. This holds for all phi element of CC1 of continuous function, C1 function with compact support in omega. C1 function with compact support in omega, or all function for which all the partial derivatives exist and are continuous, and they vanish near the boundary of omega. Okay? So I say that u is so omega b is an open set, u is a locally integrable function, and I say that v element of L1 log omega is the weak ith partial derivative of u if u into d phi by dxi is equal to minus integral over omega v into phi. This holds for all phi. Okay? When omega is in AB, interval in R, this is exactly what we have motivated in the just now. Okay? So this is the definition of a weak derivative. Okay? So look at very carefully. I have started with a function u. Then we say that v element of L1 log omega is the weak ith partial derivative of u. Okay? So next question is, suppose u, before that maybe the first, I will write it as, the first remark is weak derivative if it exists is unique. That means there can be at most one weak derivative. Okay? That means what I want to show you, suppose there exists two weak derivatives say v1 and v2. Okay? Then what do I have? Then I will have integral over omega u into d phi by dxi is equal to minus integral over omega v1 into phi. Okay? And we also will have integral over omega u into d phi by dxi. Okay? That's going to be equal to minus integral over omega v2 into phi. These both relations holds for all phi element of CC1 of. Now you can combine these two relations, and this will imply that integral over omega, I can put v1 minus v2 this into phi equal to 0 for all phi. This, as before, this will imply that v1 minus v2 equal to 0, or equivalently v1 is equal to v2. Okay? So that shows that if there are two v1 and v2 satisfies the same relation, then v1 has to be equal to v2. Okay? So if the weak derivative, if it exists, it is called, they are going to be unique. There can be at most one weak derivative. Okay? Now the next point here is that what I wanted to talk here is what is the relation between, now next remark. Suppose u is in, say, C1 function in omega, then you know that du by dxi will exist and is continuous. Is the unique weak derivative. So we know that weak derivative, if it exists, is unique. So it is enough to show that du by dxi is the unique weak solution. Enough to show that du by dxi is a weak solution. That follows just from the integration by parts, right? So this is the relation I want to, u into dphi by dx is equal to minus, by integration by parts you will get minus du by dxi into phi. So that is the only thing, okay? So we know that, so weak derivative if xs is unique, okay? But the next remark is that weak derivative may not exist. Yeah, maybe I will give you an example first. Example. So I am sure one of the function which you know for which the weak derivative, which is not differentiable, one of the first example you know is u of x is equal to, say, mod x, or x is in R. Okay, this is a continuous function, and I am going to show that we know that u is not differentiable, okay, not differentiable. Okay. But we will show that u has a weak derivative. This means that u is a weak derivative. Okay. So how do I do that? So I wanted to show that. So let phi element of CC1 of R. Okay. We want to show that we want to find the existence of V. Okay. Then integral over R, I am putting it as u of x into phi prime of x. Okay. This is nothing but u of x, you know, is mod x. That is going to be integral over R mod x into phi prime of x dx. Now this I can write it as mod x. Mod x is x when x is positive and it is minus x when it is negative. So I can put it from minus infinity to 0, say minus x into phi prime of x, plus when it is from 0 to infinity, it is going to be x into phi prime of x. Okay. Now in x and in this interval minus infinity to 0, x is differentiable. So I can apply integration by parts, and when I do the integration by parts, I will get this is going to be equal to integral from minus infinity to 0. Okay. So I will have a derivative will be 1, so I will have phi of x. I will have phi of x dx, and then so you will have then the boundary term is going to be 0. X vanishes at origin, and phi also vanishes at infinity. So this is going to be this plus minus here integral from 0 to infinity phi prime of x. Okay. So this I can write it as minus integral from minus infinity to plus infinity v of x into phi of x dx, where v of x is going to be equal to minus 1 when x is negative, and it is going to be plus 1, say, when x is, or x greater than 0. Okay. So you can see. So you will see that, so that shows that we have integral over R u into phi prime is equal to minus v into phi. For all phi, we have this. This implies v is equal to minus 1 when x is negative, and plus 1 x greater than or equal to 0 is the weak derivative. Weak derivative of mod x, the function mod x. So we know that mod x is not differentiable at a point, but this weak derivative of mod x exists. Okay. So another remark I wanted to make is the derivative is a point-wise concept. Derivative is a point-wise concept. Point-wise concept, but weak derivative is not. What I mean here is that when you talk about derivative, you typically say that f is differentiable at a point. Okay? But I did not say that weak derivative at a point. It doesn't make sense. Weak derivative we will always talk about it's in an interval. Okay? So it's not a point-wise concept. Okay? That is what, for example, mod x, we will say that it is not differentiable at 0. Okay? But what I say is that the function mod x has a weak derivative. I am not saying that it has a weak derivative at 0 or some other point. No. Okay? So that's one difference here. Okay? Now another remark I want to make is weak derivative may not exist. Weak derivative may not exist in general. So that means given a function, you cannot say that the weak derivative always exists. Okay? So I'm just going to give you an example here. I'm going to show that u of x is equal to, say, 0 when x is negative, and I'm going to put 1 when x is greater than or equal to. Okay? My claim is that u does not have a weak derivative. So how do I prove that? I will assume that there is a weak derivative, then I will get a contradiction. Assume u has a weak derivative. Say that means what? That is, v is going to be a locally integrable function on R and satisfies integral over R, okay, u of x into phi prime of x dx is equal to minus integral over R v of x into p of x for all phi in C1 function with compact supporting. Okay. So I assume that there is a weak derivative v and I wanted to get a contradiction. That is what I am going to do. Okay. So I assume that there exists a v which satisfies this relation. Now let me start with the LHS, left hand side. U is the function which is 0 when x is less than 0 and 1 when x is greater than or equal to 0. So basically the integral is, integral over R u of x into phi prime of x dx, okay, that's going to be equal to integral. In the negative axis it is 0, so integral is only on 0 to infinity, there it is 1 and phi prime of x dx, okay, and that is going to be equal to, you see phi at infinity is 0, so it is going to be minus phi of 0, okay. And so the right hand side becomes RHS is minus, I don't know what it is, what is v, but it is just v of x into phi of x. dx. So LHS is equal to RHS, so that implies that, this implies that phi of 0 is going to be equal to integral over R Vx into phi of x dx. This holds for all phi in CC1 of. Now I am going to show that this is a contradiction. It's a contradiction. Contradiction, as I show you, as follows. Okay. So what I do is that I have this function defined here and I have 0 here. Okay. And I will take the interval minus 1 by n and I will take 1 by n. Okay. And I will take a function phi n, okay, such that it phi n, this is going to be 1, phi n is going to be something like this. Then it becomes 0 after. Okay. So phi n is going to be equal to, say, at 1, when phi n of x is going to be 1, when x is equal to 0, okay. And this is, phi n is going to be 0 if mod x is greater than 1 by n, okay, and then phi n is less than or equal to, and phi n is less than or, and mod phi n is less than or equal to 1. Okay. Now apply this relation for this phi n. Then you will get that phi n of 0, that is going to be equal to 1. That is going to be equal to this integral of v into phi n. So that implies the integral is from minus 1 by n to plus 1 by n v of x into, okay, you will have a phi n of x. Okay. If you know a little bit of measure theory, okay, and you can use what is known as the dominator convergence theorem, okay, from measure theory to conclude that this quantity will go to 0 as n goes to infinity. On the left hand side is 1 and the right hand side goes to 0. That implies 1 equal to 0, and which is a contradiction. Okay. So you will see that it's a contradiction. So if the weak derivative exists, that is going to give you a contradiction. So that shows that weak derivative may not exist. So the message finally is that, finally the points are, the first one is weak derivative. Okay, so let me just write, if u is C1, okay, then du by dxi is the weak derivative, is the unique weak derivative. And the second point is that weak derivative may not exist in general. Weak derivative may not exist. Not exist in general. And the third point is that, if the weak derivative exists, it is unique. Yes? So the notation is, I am going to use a notation now. Notation for u element of L1 log omega. We will denote du by dxi. We will denote by du by dxi the unique weak ith partial derivative. Partial derivative, of course, if it exists. if it. So from now onwards, whenever I talk about du by dxi, that it does not mean that the partial derivatives exist in our classical sense. It only means that the weak derivative exists. Of course, if classical derivative exists, then it is weak derivative exists. But in general, weak derivative may exist even if the function is not differentiable, like what we saw in the example of mod x. Okay? So in general, now, du by dxi, my notation is a weak ith partial derivative. Okay? So that is the thing. So once I have this notion of weak derivative, I can define the Sobolev space. Okay? So I can define what is known as a Sobolev space. Sobolev space. Sobolev space. Let omega be an open set in Rn. Set in Rn and 1 less than or equal to p less than or equal to infinity. We define, or maybe I will define open set in Rn. Okay. We define the Sobolev space. I will call it as h1 of omega. As h1 of omega is equal to all u which are in L2 of omega. That means all square integrable functions such that du by dxi is also in L2 of omega for I is equal to 1, 2. That means what is h1 of omega? That implies that it's a subset of the space L2 of omega. L2 means all functions u for which integral over omega mod u square is finite. Okay? h1 of omega is a subspace of that, which is called h1 of omega is all u in L2 for which all the partial derivatives, weak partial derivatives will exist. Okay? That is du by dxi will exist. And that is also in L2. Okay? So that is the condition. And then I can define a norm here. Define a norm. Then h1 of omega by. So I will take two functions u and v, and I want to see what is this h1 in a product. Okay? Oh, sorry. Define a norm in h1 by norm of u. U is going to be integral over omega, okay, modulus of gradient of u square all to the power 1 by 2. Okay. So where gradient of u is nothing but du by dx1, the vector du by dx1, du by dx2, etc., and du by dx. Okay. And modulus of gradient of u is nothing but the Euclidean norm of that. That is, so mod x is, so it is going to be summation I equal to 1 to n modulus of du by dxi square all to the power 1. This is the Euclidean. Okay. So that is what so it's a natural condition. It basically says that h1 of omega is all L2 functions whose weak derivatives are also in L2. So there are two conditions for a function u to be a member of h1. That is, function has to be in L2 and then derivative also has to be in L2. Okay, yeah, definition is not complete, so I have to gradient of u square plus, sorry, I did not complete the definition. This plus integral over omega, you can put u square here. Definition is this plus integral over omega u square and then all to the power 1. Okay. So L2 norm of u plus L2 norm of the gradient, that is going to be the norm in this space. Okay. Then you can show that, you can show it's a theorem, which I am not going to prove it because we don't have the time. Okay. You can say that H1 of omega is a Hilbert space with the norm, with the inner product of u with v is going to be equal to integral over omega gradient of u dot gradient of v plus integral over omega u into v. Gradient of u dot gradient of v, that is the usual dot product of vectors, and then and you can see that inner product of u with u, that is inner product of gradient of u with u, that is nothing but integral over omega modulus of gradient of u square plus integral of u square, that is exactly the norm square. Okay. So, and it's not very difficult to show that it's an inner product. Okay. And you can actually show that it is going to be complete. Okay. So the basic tools which you are to use here is the LP spaces or L2 space is a Hilbert space. Okay. LP spaces are complete. If you know that, then this can be very easily proved. So if you have followed a course on measure theory, you can, it's not very difficult. You can try to prove the same results here. Okay. So basically you understand that this H1 of omega are all collection of L2 functions whose derivatives, which are taken in a weak sense, they are also in L2. Okay. So that is what the thing. Okay. So now you remember when when we were talking about functions earlier, the problem in the morning, we were talking about PD is like minus u second is equal to f. Then there used to be boundary conditions like u at A is equal to u at B equal to 0. That means there is something which is vanishing. Okay. So that means the boundary, you have to take some functions for which the boundary value is 0. Okay. So there is a way of defining or a subspace of this H1 of omega whose boundary value in some sense is 0. Okay. So that is what I am going to do next. Next remark. The first one is, so the C infinity functions with compact support in omega, okay, which is a subset of C1 function with compact support in omega, and which is a subset of this space H1 of omega. Okay. Because C1 function with compact support means derivatives are continuous and they are bounded, therefore naturally they are square is integrable and so on. Okay. So this is a very easy checking. Okay. So now you see that you have this kind of CC infinity of omega, some contained here in H1 of omega. Okay. And this is a norm linear space with a norm of equal to integral over omega gradient of u square plus integral over omega u square all to the power. So you have a subspace of this space. So you can talk about the completion of that. Okay. So definition. We define H1 0 of omega as the completion of, say, CC infinity of omega in H1 of omega. Okay, so that is the thing. Okay, so in fact you can see that in the morning I defined something like an H1 0 of AB. Okay? And in fact that is going to, this is actually going to be equal to this H1 0 of omega, which I defined like this when omega is AB. Okay? It requires some little work to do that, but it's not that complicated if you are studying things in a very systematic way. Okay? So what I wanted to tell you is that, so you have now two spaces, one is H1 0 of omega, and which is sitting inside H1 of omega. Okay? This is a Hilbert space. Hilbert space. Okay? And this is a subspace of that. Because it is complete, so it is going to be a subspace. Okay? So now in the morning, again recall, in the morning I proved an inequality like this. Integral of from A to B, u square is less than or equal to a constant times integral from A to B, u prime square. Okay? So there is a similar inequality here, and what is known as the Poincare inequality. I will write this theorem. It is Poincare inequality. The proof is also somewhat the same as what I did in the morning for this kind of an inequality. So it says that let omega be a bounded domain, in Rn. Okay. Then there exists a constant C depending only on omega, such that integral over omega u square is less than or equal to constant times integral over omega gradient of u square. Okay? For all u element of H1 0 omega. Okay? So this is what we have. So morning what we have showed that u square is less than or equal to u prime square, right? Integral of u square can be controlled from above by integral of u prime square. Now in the higher dimensional, the theorem is that integral of u square can be controlled from above by integral of gradient of u square. Okay? So this is the corresponding inequality, and the proof is also somewhat similar. And if you know that, if you understood that idea, and if you know some measure theory and a little bit of mathematical maturity, it's not very difficult to prove this inequality in the same way. It is not very difficult. So I have defined this H1 0. Okay. The whole idea of the remark is that okay, H1 0 omega are functions in H1 of omega with boundary value 0. Boundary value, I am putting it inverted comma, boundary value 0. Okay. This H1 0 omega is a function which basically vanishes on the boundary. Okay. So actually you cannot, there are difficulty to talk about the boundary value. There is a theory dealing with that. You can justify, because the problem is that all these L2 functions, everything, they are all equivalence class of functions which are defined only almost a variable. So you cannot restrict to on subspaces which are of measure 0. So for that you cannot directly talk about boundary value, but there is a way of making sense of that, and you can talk about that. Just try to understand that in a generalized sense, h10 of omega is all functions in the sublow space h1 for which the boundary value is 0. Okay? So once I have this much, I can try to talk about the Differential problem. Differential problem. So I am going to define, let omega be a bounded open set. Let omega be a bounded open set in Rn, and consider the problem, consider the PDE, okay, minus Laplacian of u is equal to sum f in omega with u is equal to 0 on boundary. Okay. So then again, as before, if u is a solution, that means that u is C2 and satisfies the PD. Okay. If u is a solution, then for any phi element of C1 function with compact support of omega, I can integrate this minus Laplacian of u, this into phi equal to f into phi. Then I can integrate this thing over omega. Okay. Then after that I can integrate by parts, and then this will become integral over omega gradient of u dot product with gradient of phi, that's equal to integral of f into u. Okay. Now, as motivated in the one variable case in the first lecture, a function which satisfies this kind of an identity, we will call it as a weak solution. Okay. So that is what I am going to, again, in the morning I started weak solution as a function which is differentiable once. In the end, I end up defining it in the space h10 of AB, because that is where I could find it. Here the corresponding space is going to be h10 of omega. Okay. So I will define it formally, definition. Okay. Let omega be a bounded open set in Rn, okay, and consider the problem. So the problem say minus Laplacian of u is equal to f in omega with u is equal to 0 on boundary of omega. Okay, where I assume that f is in the L2 of omega. Then we define a weak solution. A weak solution of this problem. As a u element of the space which I defined before, h10 of omega, satisfying integral over omega gradient of u dot gradient of p is equal to integral over omega f into p for all p in h10 omega. Okay. So we define a weak solution of this problem as a function u in the sublow space h10 of omega, which satisfies this kind of an identity. For all, this has to be true for all phi in h10. Okay. Then exactly as before, I can prove a theorem, which tells that weak for a given f, for a given f in L2 of omega, there exists a unique weak solution. So again, the proof is exactly like what I did before. It is using the representation theorem. Okay. So what you have to do is that the first step is define say L from H10 of omega to R by L of phi is equal to integral over f into phi. Okay. Then you can see that then modulus of L of phi, okay, this is going to be modulus of integral over omega f into phi. You can apply the Cauchy-Schwarz inequality and you will see that this is norm of f, that is the L2 norm, and norm of phi in L2. F is fixed, so I can write it as a constant, and this is nothing but, and I have the Poincaré equality which controls the, where is it? Yeah, I have proved that L2 square integral can be controlled with the square integral of the gradient. So I can use that, so you will get that this is going less than or equal to integral over omega gradient of u square to the power 1 by 2, okay, which I can write less than or equal to, say, so constant into integral over omega. I can add one more term here, gradient of u square plus integral over omega u square to the power 1 by 2, and this will imply that this is nothing but c into, this is the norm of u in H10. So this will imply that L is in the dual space of H10 of omega, okay, and then you can apply the representation theorem, okay, and when you apply the representation theorem, you have to observe one fact. So the inner product in, H1 is inner product of u with v is integral of gradient of u dot gradient of v plus integral of u into. Okay. Now H10 of omega is a subset of H1 of omega. So here there is an inner product, so the same inner product will be here. But what one can show is that using Poincaré inequality, okay, we can show that integral over uv or u phi going to integral over omega gradient of u dot gradient of phi is an equivalent inner product. Inner product in H10. So you use these facts and then just write down, you will see that there is going to be a weak solution. Okay. So what I have seen here is that I have this problem like minus L plus in u equal to f and u is equal to 0. This is in omega and this is on boundary of omega. It's a boundary value problem. If f is in L2, for example, I have a weak solution. Okay. For example, now suppose I assume that f is better, suppose f is in continuous function in omega closure. Okay. Then you can, in fact, you can show that the u is the solution, the weak solution u is actually, you can prove that C1, and in fact it is known as what is known as C1 alpha. Okay, what is Helder? First derivatives are also Helder continuous. Okay. And if f is actually what is known as the Helder continuous function, C0 alpha of omega closure, whatever it means, then actually you can show that this implies that u is actually in C2 of omega, and solves minus Laplacian of u is equal to f. So in this kind of solving these kind of equation, there are two steps generally. One is find a weak solution. Okay, there we use some functional analysis and all something. And here you can see some of the statement. If the right hand side is better, like it has some smoothness, okay, then the solution is also becomes much better. That is what I said. If f is continuous with some property, for example, if f is C1, then you can show that there is theory to show that the weak solution which you found is, in fact, it is C2, and it's a classical solution. Okay, so the strategy is twofold. First, find a weak solution. Then, after trying to show that this weak solution is indeed classical solution. Okay, so this part, whatever I am talking about, it comes under broader discussion, what is known as the elliptic regularity theory. Okay? So you need various things to do that. As you can see, I have been using a lot of measure theory in the all things, functional analysis, and when you are going to do these kind of parts, you will be using a little bit of harmonic analysis, more functional analysis, and so on. Okay. So I just wanted to show that when you study this PDE in the modern framework, a lot of analysis from various branches are going to be used here. Okay. So I think I will stop here today, and tomorrow in the two lectures, I will try to study a little bit of nonlinear problems. Basically something like minus Laplacian of u is equal to, say, some u square, or in general something like f of u. Okay? So what I am going to do is that I am going to give a brief introduction to calculus of variation and trying to connect with these things, and you will see that more mathematics is involved in. Okay? So you will have more functional analysis, even some topological aspects will be coming to picture, and you will see that just a flavor of some modern day things. Okay. So today whatever I talked about was for linear equation. For example, when I put here u square, it becomes nonlinear. Okay, or general f of u and so on. So tomorrow I will give some brief introduction to calculus of variation and its connection with some of these problems, and then how do you try to these kind of problems. I will give some brief idea. Okay. Okay, so I will stop here and we will continue tomorrow. Any questions? I will be happy to answer.
So, if there are no questions, then let us thank Professor Sandeep, and we look forward to hearing him tomorrow at 9:30 again. Okay.
Okay, thank you.
We have only 5 minutes. Right?